Consider the pH of a solution of 0.42 molar hydrochloric acid. Now, hydrochloric acid is a strong acid. That is, it dissociates 100% in solution. So, if you have 0.42 molar hydrochloric acid, ultimately you'll have then 0.42 molar of the proton or hydronium concentration within the solution and 0.42 molar of chloride. So, being that it's 100% dissociation, we have the same concentration of protons as of this monoprotic acid. And so we can find the pH is equal to the negative log of the concentration of protons, or negative log of 0.42, or 0.376 molar. What is the pH of a 0.234 molar barium hydroxide solution? Now, barium hydroxide involves barium, which has a 2+ charge, and hydroxide, which has a -1 charge. And so a barium hydroxide has 2 hydroxides on the barium, and that's going to have important implications for the pH of the solution. Barium hydroxide is also a strong base, and so it dissociates 100% in water. So if we have 0.234 molar barium hydroxide, we'll have 0.234 molar barium ion in solution, and twice 0.234, because we have a coefficient of 2 here, there are twice as many hydroxides being released as barium hydroxides are dissolving. So we get twice 0.234, we get 0.468 molar hydroxide solution. And so in order to determine the pH of that solution, where right now we only are given the hydroxide concentration, we have the option of finding the proton concentration and then the pH, and that would require that we're taking the fact that Kw, or 1.0 times 10 to the negative 14, is equal to the concentration of protons times hydroxide. Now, this is a little bit awkward because it involves multiplying or dividing this 10 to the negative 14. What's easier, though, is to go via POH and then into pH, because that just involves the fact that pH plus POH is equal to 14. It's a lot easier to subtract the pH from 14 to find POH. And so find the POH from our concentration of hydroxide. So the POH is 0.329. Then find the pH, that's 14 minus the POH, that's 13.67. Now, these are simple cases in which we have strong acid or base, but what if we're dealing with a weak acid, or in a later video, weak base? So consider where we have 0.312 molar hydrofluoric acid, a very similar concentration to our hydrochloric acid example up top, although this time that hydrofluoric acid is a weak acid. It has an equilibrium constant. Because it's a weak acid, it does not dissociate 100%. In fact, generally, it will dissociate about 0 to 5% of the time. Find the pH from that hydrofluoric acid solution. So you want to find the pH of that hydrofluoric acid solution after equilibrium is reached. So you need the equilibrium concentration of protons in that solution. And so you'll need to build a nice table and consider that the hydrofluoric acid is going to have some loss in concentration, and the proton and the fluoride concentrations are going to have some gain, and so you'll get the following. And then we can plug into our equilibrium expression. Ka, which was given to us here, is the equilibrium constant for some acid, generally HA, dissociated into a proton and its conjugate base, A-. In this specific case, it's HF going into proton and fluoride. Now, the Ka is 7.1 times 10 to the negative 4, so plug in the concentrations of protons, that was X, and fluoride, that was X, so we get X squared here, and then plug in the concentration of HF after equilibrium is reached, that's 0.312 minus X. Now, this is a fairly ugly problem right now. As we saw in the last chapter, it's a pain to deal with quadratic equations. Now, we're actually able to avoid quadratic equations sometimes by making presumptions. You see, in the previous chapter, a lot of the time, our equilibrium expression, our constant, had some very large or very small number. So perhaps 10 to the 20 or 10 to the negative 30, where the change in the concentration of our reactants and products was very significant. But in this case, in this chapter, where we're dealing with acids and bases, oftentimes our Kas or Kbs are going to be not so big or small. So if we're dealing with perhaps 10 to the negative 6 to 10 to the positive 6, there's not going to be as large a change in the value of x. Well, actually, more likely, 10 to the negative 6 to 10 to the 0. There's not going to be as much of a change in the value of x. And so sometimes that value of x will be insignificant. And considering that, we should be able to cancel out that value of x and therefore be able to avoid the quadratic equation and save ourselves a lot of time. Okay, just realizing, yeah, it's probably best to consider that x is able to be canceled if it's about negative 20, 10 to the negative 20 to about 10 to the negative 4. If you have, say, 10 to the negative 2, x becomes quite significant. Okay, so, but the best way to consider whether you're going to cancel out x is to cancel it, scratch it out, considering that it might be insignificant. Then determine the value of x by avoiding the quadratic equation. If x is less than 5% of the initial molarity, then it can be canceled because it's a relatively insignificant amount. So in this case, cancel out x. All right, so we're able to avoid the quadratic, simplify, we get x is equal to 0.0149. Now here, x, if it's less than 5% of the initial molarity, then it was able to be canceled. But if it was greater than 5% of the initial molarity, then it could not be canceled, and we must redo the problem by using the quadratic. So let's test. What is the percent ionization? What percent value of the initial concentration of our acid is actually dissociated and therefore giving a certain concentration of protons? Percent ionization is the concentration of protons after equilibrium over the initial concentration of our acid times 100%. So plug in our value for x, which was 0.0149, over the initial concentration of our acid, 0.312, multiplied by 100%. That's 4.8%. If your percent ionization is less than 5%, then you can move on to the rest of the problem. It was okay to cancel out x. However, if it were greater than 5%, then you would need to redo the problem, not canceling out x, and you'd have to use the quadratic. Okay, so it was okay to cancel out x, so move on. What's the pH? Well, plug in that the concentration of protons is equal to x, which is equal to 0.0149 molar, and so you find that the pH is 1.83. Compare this value when we had a concentration of HF of 0.312 to the pH when we had a concentration of hydrochloric acid about the same molarity as HF, 0.42 molar. Now, if we had the strong acid, we had a pH of 0.376 molar, not molar, 0.376. But if we're using a weak acid, our pH is 1.83. So this is over a 10 times difference in the concentration of protons, because that hydrochloric acid dissociated 100% and gave a lot of protons in solution, but HF, even though we had a similar concentration of it, dissociated only about 5% and did not give as many protons in solution. So weak acids generally will not give a very acidic solution. So for example, you have vinegar, which you can find in your salad dressing. That's about 5% acetic acid, CH3COOH. Now, if it were 5% hydrochloric acid, it would be extremely dangerous to drink. You would really damage your throat. But being 5% a weak acid, it's not that dangerous, and therefore we can use it in our salad dressing. So consider another example where in our previous case we had 0.312 molar HF and we got a percent ionization of 4.8% and a pH of 1.83. What happens if we have a much higher concentration of HF? 10 times higher concentration. What will be the pH and the percent ionization? So if you repeat all the calculations as before, you'll find that the pH is a little bit lower. It's 1.32 instead of 1.83. So it turns out that the concentration of protons is not 10 times higher as you might expect, having 3.2 molar instead of 0.312 molar. In fact, the concentration of protons is only, let's see, 0.0149 versus 0.0476. The concentration of protons is only about 3 times higher, even though we had 10 times as high the concentration of acid. Even though we have 10 times as much HF, we only have 3 times as much protons in solution after equilibrium. That's because the percent ionization changes as the reaction proceeds. Actually, as you have differing concentrations of HF. Having much higher concentration of HF, our percent ionization is actually much lower than in the previous case where it was 5% ionization. As you have an increasing concentration, your percent ionization decreases. This is because if you have a very low concentration of your acid, the dissociation of HF is unaffected by the concentration of other HFs, but the combination of H and F to give us HF is affected by the concentrations of nearby H's or F's. So if we have a much higher concentration of HF, then we have a lot more proximity between H and F, and therefore they'll collide quite a bit more frequently than in a less concentrated scenario. And so that drives the rate of the reaction to the left to be much larger, and hence will drive the equilibrium more so towards the original molecule. Thanks for watching, guys.